So for today's assignment, we'll be discussing the basic equation of statics, which is represented by dP, which is displacement of pressure, over dz, which is displacement of distance. In this case, we're going to call it altitude, equal to negative rho, which is density, times g, which is gravity. For this scenario, we could be talking about a piston, so just draw a quick diagram. So let's say that this location right here is Z1, and this location down here where it stops is Z2, and so that whole distance we can call H. So for now, we'll leave those undefined, and we'll just do the equation. So first, we're going to move this dz over to the other side so that we have dp equals negative rho g dz. And from here, we're going to take the antiderivative of both sides. So this will be from P2 to P1. This will be from Z2 to Z1. And then, so from there, we can call this location 1 and this location 2 for the P's over here. From there, that's going to leave us with P from P2 to P1, and that's going to be equal to negative rho g z, and that's going to be from negative h to 0 since we're moving downwards. And we can call this P1 the absolute value of pressure at sea level, which is 1,001,325 pascals. So from there, we're going to start plugging in numbers. So this will become P2 minus 101,325, and that will be equal to rho GH. These negatives cancel and become positive. From there, we will bring this 101 over. So we'll have P2 equals 101,325 plus rho GH. So essentially, we have P equals rho GH. And so from here, we're going to take the ideal gas law, which says that PV equals nRT, and we're going to apply it to this situation with rho. So in this case, it's going to say that rho equals P times V over RTN. And so that this V and N then becomes the molar mass, which is represented by M. So we'll go back to the equation that we have, and we'll say that dP equals negative P times M over RT times G times dZ. And then we'll do the antiderivative again of both sides from P2 to P1, Z2, Z1. And that will end up leaving us with 1 over P dP equals antiderivative of this from negative mg over RT, because we move the P over, and we'll have dz there. And so if we go further, I got to flip the page. That'll leave us then with natural log of P2 over P1 equals negative mg over RT times delta z. And so from here, if we move everything over and we take the exponential of both sides, that'll cancel this. And so we'll be left with P2 equals P1 times the exponential of negative mg times delta z, which is Z2 minus Z1, all over RT. And so a few examples, apply this equation to calculate air pressure at varying altitudes, assuming constant temperature. We could call, let's say, Z2 equals negative 10 meters and Z1 equals 0 meters. So we can plug in P2 equals, P1 would be the P absolute, so that would be the 1,001,325 pascals. That'll be times E to the, we can ignore the mg and the RT because those would all be constant for all the scenarios. And so then we'll be left with negative 10 minus 0, so that'll leave this as negative 10. And so if we plug that into a calculator real fast, we'd see that e to the negative 10 times 1,025, that P2 equals about 4.60. And so let's do that again, but let's say Z2 equals negative 20 meters and Z1 is still equal to 0. We would do P2 equals 1,001,325 times e to the negative 20 this time. So if we plug that into the calculator and then we multiply, we see that that's equal to about 2.088 times 10 to the negative 4. So as the pressure is as the altitude is increasing, in this case you could say decreasing because it's becoming more negative, the pressure is decreasing as well. And so that's how you use this basic equation to solve different varying altitudes.